Good afternoon, everyone. This is Marissa Waterman from the American Academy of Environmental Engineers and Scientists. Today, we have our friends here from CDM Smith and Metropolitan Sewerage District. They'll be discussing their recent project on sewage, sludge, incinerator improvements. And Richard, we're ready when you are.
Thank you, Marissa. Good afternoon, everyone, and welcome. My name is Richard Sang. I'm with CDM Smith. I've been with them for 30 years and primarily focusing on doing residuals and biosolids work. I will start things off today. There will be 3 other presenters, and they will introduce themselves before they speak. I'll start off with some project background. Hunter Carlson will speak on pilot testing and construction, and Frank Sapienza will then discuss design and permitting, and we'll wrap up with Ryan on the operation and maintenance of the system. So with that, let's get into it. First, project location. This project we did for the Metropolitan Sewerage District of Buncombe County. Just give you an idea what Buncombe County is. A beautiful western part of North Carolina near Asheville, part of Blue Ridge Mountain. Let's see. Okay. So some background on project drivers. Basically twofold. One is regulatory, and the other is maintenance because of the aging equipment. So a little background. Up until around 2007, sewage sludge incinerators were not regarded as solid waste by EPA. So they are regulated a little differently. Under Section 112 of Clean Air Act, due to lawsuits brought by environmental groups, and the court eventually ruled the EPA need to comply and revise its definition of sewage sludge as a solid waste. So instead of regulated under Section 112, it goes under Section 129 of the Clean Air Act, which is a lot more stringent, and it requires all incinerator to utilize emission controls, which reflect the maximum degree of emission reductions, referred to as the MAX standard. So it's basically, follows some of these regulatory requirements, which I won't get into detail, but the final compliance requirement was May 2016. So the plan is a 48 million gallons per day plan in Asheville. They have 1 4-dies bed incinerator unit. It was started up in 1992, designed for 40 dry tons per day capacity. It was equipped with quenchers, Venturi scrubber, and tray tower scrubber. There were some minor repair made in 2003, primarily fixing the refractories, heat exchanger, fluid dyes, air blower, so on and so forth. So since all the changes, the cost of all the changes was less than 50% of the escalated equipment cost, the incinerator was classified as existing units. So looking at some of the emission testing historically, comparing to the MAC limits that they have to comply by 2016, shown on this table here, the number of parameters we need to look at, but I draw your attention to two major ones, basically mercury and SO2, where this stack testing has shown that they will not be in compliance. So the focus was in dealing with these couple of parameters. So we started the project based on the stack test results to provide improved control of PM, particulate matters, and the metals. We placed the existing Venturi because they're corroded, and tray scrubbers with multi-Venturi scrubbers, and then install a carbon-based type of mercury control system. So we started and get into preliminary design. Shown here, we sketch out because the mercury-based control system, the carbon absorption system for mercury control, it pick up quite a bit of space, so there's no space in the the existing building to accommodate it, so it needs to be set outside. The carbon absorber system can achieve very low emission of mercury, so it's quite effective. Also have benefit of removing some of the other organics. However, it's quite expensive as we look into it. At that time, the estimated capital cost was a little over $10 million. Also takes a lot of space, as I've shown you. And we also need to install another heat exchanger between the primary heat exchanger and quencher to reduce the humidity in the flue gas in order for it to be effective. In addition, we were looking at replacing the air blowers because it also added significant pressure drop to the system. And finally, obviously, the carbon will spend over time, and they need to be disposed of as hazardous waste potentially. So as we're looking into that, MSD and us were brought to attention with another emerging technology called the Sulfur Polymer Composite system. Also, actually offered by EnviroCare, the company who was going to provide the multi-Venturi. It was brought to our attention that some pilot tests was done at another utility, and it's shown promising results. So the Sorbent polymer composite, it's really just a filter membrane, fairly simple, composed of polished sulfonated polymer, manufactured by WR Gore system, sort of similar to my Gore-Tex raincoat, if you will. So given that information, MSD decided to conduct some pilot testing of this new technology. Hunter.
Okay, thank you, Richard. This is Hunter Carson with the Metropolitan Sewage District. I'm the Assistant Director of Engineering here and served as the project manager on the Incinerator emissions upgrade project. I'll talk about the pilot scale testing now. Because of the strict timeline that we were up against to meet the MACT compliance schedule of March 2016, we had to progress with the carbon-based system that was sort of the tried and true method. So CDM was progressing with that design as we learned more about the mercury or the SBC system and the cost. It's approximately, in our experience, about 10% of the carbon-based system that we were looking at. So we wanted to pilot tested. We discussed this with EnviroCare in January of 2014 for the 2 months that we pilot tested, which was July and August of 2014. It's about $30,000 to run the pilot. We then had to complete sampling for the mercury, which we utilized Element 1 engineering out of Colorado. And of course, the goal of the pilot scale was to meet the MAC limit of 37 micrograms per cubic meter. Next slide. So a little bit about the pilot demonstration itself. It was furnished by Envirocare International. It was a slipstream, approximately 30% of our normal flow through the incinerator, or about 1,800 cubic feet per minute. We used a 5-layer design, and this was based on some of the inlet load concentrations that had been measured in historical testing events. The highest concentration that we had seen to date was 120 micrograms. So based on that inlet loading, Envirocare expected a removal efficiency of about 75%, which would get us down to 31 micrograms, which would, of course, be under the MAC limit. In the lower right there, you can see just a schematic of the pilot scale itself. We tapped into the exhaust ductwork out of our incinerator. It was vacuumed through via a ID fan or blower, which drove it through the unit itself. We had 5 SPC modules inside the unit, and then it was delivered back into the exhaust stream. Next slide. So the proposed pilot schedule was pretty straightforward. We had 3 days to install it and get it running. And then Envirocare suggested that it should be run unmanned for 4 weeks to sort of break in these new SPC modules. So sounded pretty straightforward. We figured that we'd be testing in the middle of June. That was a little different, which I'll explain in the next couple slides. This is the pilot unit itself, essentially just a stainless steel box, but it did house the 5 units plus a mist eliminator. Just for scale, it was 8 feet tall, about 6.5 feet wide. We did have to set it on the 3rd floor of our incinerator building, which is where the exhaust stack is. So we had to set it with a crane. On the right side, you can see the setup. It was just flexible hosing that went to the suction blower and then through the unit itself and then back into our exhaust system. I do want to bring focus to the flexible tubing itself there. This was the initial setup, and as you can see, a lot of that ductwork is sloped back towards the blower fan, which ultimately caused us a lot of issues, and I'll talk about that here in the next couple minutes. Next slide. So I told you about the proposed schedule. The actual schedule for trying to run for a total of 4 weeks actually ended up being 7 weeks, and it was heavily manned by MSD staff here, sometimes even 24 hours around the clock, trying to prevent problems with the unit. But we did stick with it and found received good results. Next slide. One of the biggest problems that we've experienced was the very acidic gas stream that flows through our incinerator system and out the exhaust stack. During the process of this slipstream pilot demonstration, we actually went through 3 blower motors. And the first of which, we figured it came with the pilot demonstration or the pilot unit itself. We assumed that it was an old motor, and within a couple days it seized up. So we here at MSD replaced the motor, which lasted literally 2 days, and that motor seized up. So what we were finding, as you can see on the lower left there, the very acidic, corrosive nature of the gas coming through the system was running into the blower, running down the blower shaft itself, and getting into the motor bearings, which was just destroying them. We also went through 1 or 2 fan wheels during this exercise before we really learned what the problems were. Next slide. So we were constantly tweaking the system as we were learning about it. I did mention a couple slides ago, if you paid attention to the slope of the blower discharge, we basically elevated that, sloped it back towards the pilot unit itself so that we wouldn't get drainage back into the blower unit. Once we made that improvement, we also added a condensate drain to the suction side of the blower. Once we made those two improvements, the pilot ran like a dream, and we were able to test. So after actual 4 weeks of runtime, which again took us 7 weeks to get there with all of our ups and downs, but we did make it July and August. We performed 2 sampling events. We tested for both mercury and sulfur dioxide. The SPC media was marketed by W.L. Gore as being able to remove sulfur dioxide in addition to the mercury. So we wanted to test that since we were close to meeting, actually over the SO2 MAC limit in some of the historical testing that we had done. So we utilized E1E to come and set up 3 continuous mercury monitors. We completed testing continuously over 24 hours for 5 days in July, and then also supplemented that information with sorbent trap testing, which you can see that unit in the far right, the big testing probe, which actually you can see it there taking one of the inlet concentration measurements, and the picture kind of in the center below that is the actual carbon sorbent trap testing device. Next slide. So after we had run the pilot for a sufficient amount of time, W.L. Gore and EnviroCare came back to actually test the media. That is a sample of the media that you see there in the center photo, the SPC. Their sheets, as Richard mentioned, kind of look like a very heavy Gore-Tex rain jacket material, but they clipped a sample of that media, tested it for the mercury loading, and were able to give us an estimated media lifespan, which was ultimately estimated to provide about a 24-month guaranteed lifespan. So this is some of the testing data. This is the continuous monitoring results, and in the dark blue you can see those are the inlet concentrations over the 5 days that we tested. We did spike at over 100 micrograms per cubic meter. However, over the course of the 5 layers, you can see the dark pink data on the bottom. We were having a effluent or exhaust concentration in the single digits, so we were observing very high removal rates. Next slide. Can you go back one? I think we just skipped one. There you go. This is just the, yeah, there you go. This is the tabulated data. You can see our average concentration over the 5 days that we tested was about 78 parts, and we were leaving the unit at an average concentration of about 4 parts, 94% removal. As I mentioned, we did utilize carbon trap just as a verification of the CMMs, and we found that data to be consistent at 93% and 88%. As I mentioned, we did test for SO2 as well, since that was a MAC limit, and historical data had suggested that we would not be able to meet that without treatment. So you can see inlet concentrations during the testing period were right around the MAC limit. We did observe that the SPC media was capable of removing SO2. As you can see from the data there, the sort of beige color was the effluent concentration or exhaust concentration, which easily met the MAC limit. SO2 removal was also evident in the washdown water. You can see that pH probe with a pH of about 1 in the washdown water. We had a drain coming out of the pilot unit, and you can see how it deteriorated the concrete just over the course of those 2 months. So definitely did remove SO2 in the form of sulfuric acid. This is just another visual of the testing data. You can see prior to Module 1, we were around 100 parts and came out in the single digits after Module 5. So overall, mercury removal was about 94%. Overall SO2 removal with the SPC media was 82%. And after seeing this data, MSD felt that this was a proven technology, and we requested that CDM change their design to start designing around the SPC system rather than the carbon-based system. So with that, I'll hand it over to Frank Sapienza.
Hello, this is Frank Sapienza. I'm a principal engineer with CDM Smith, and we'll talk here about the design and permitting of this unit. So here we have a slide that shows schematically the wet scrubbing system consisting of a tray scrubber and then the multi-Venturi tubes. These are the EnviroCare Venturi tubes above the trays, the scrubbing trays. Then we had, above that, we had a separator stage because we wanted to separate that acidic wash water off the media above the trays, which would come down. So we collected that acidic wash water separately. and then above that, you see the SPC modules, which were arranged on the top section of the scrubber. And above that, we had a mist eliminator. This is all in one vertical unit that was constructed. Next slide. So here's a close-up of the wet scrubbing system. This is the multi-Venturi pack scrubber by EnviroCare. You see on the left there first the quenching section, followed by the trays on the bottom, and then the Venturi pack scrubbers there, the Venturi tubes. This is a high pressure water is injected at the bottom of the tubes, as much as 250 psi. We pressurize the water to atomize it so that we can get good particulate and metal removal. And the gas stream just flows through those tubes and then upward through the column. Here's some more shots of the scrubber system. On the left, you see the bottom. There's some ash pumps, and then the trays above it. But on the right, you can see the outside of the multi-Venturi tubes there. These lances that go across the media, and then above that, we have the mercury control modules. Next slide. Here's a close-up of the Venturi and the throat spray lances. Okay, this is where the high-pressure water is introduced. Whoops. And we have the water is strained before it goes into those lances. Could you back up a minute? Okay. And yeah, we have arrangement there so you can remove the lances and clean them, which is periodically done because you have to keep them very clean, these lances. Next slide. So at the bottom of the vessel, we have ash pumps and an ash thickener. The wash water from the quencher section goes to these ash pumps. It contains most of the ash. It comes out in the initial quenching, and it is then pumped to this thickener, and from the thickener it gets pumped to ash lagoons. Now, on the top section, this is where we have the SPC modules. You can see on the right, we have these boiler doors. We put these specially designed doors so that we can easily access the modules. You open up the door and get in there, and you see the modules on the left. The floors is blanked off, so the gas stream has to go through the modules at each of these stages. On the right, also, you see these letters on the side. Those are and access ports. This is where we can insert a probe to do our carbon trap sampling. You can see the actual carbon lance there in the middle of the photo there on the left. Here's a view of the carbon trap sampling probe. The actual tip of this on the right there, there's a carbon coupon which absorbs the mercury. A known quantity of air is actually pulled through the tubing, and there'll be a vacuum pump on the other end, which draws a known amount of flue gas through the tubing, and absorbs so much mercury. And then we take the coupon out and measure how much mercury is in it. And knowing the quantity of mercury and the gas flow rate, we can figure out the concentration of mercury in the flue gas at that sample point. So there were additional improvements to the incinerator during this project. Turned out that the roof of the existing incinerator was not in very good condition. We had sprung a leak. We did put on a new roof. We also replaced the incinerator exhaust duct, which you can see there in the photo on the right. That whole duct was replaced. And we replaced the primary heat exchanger. It had seen some pretty severe corrosion in the heat exchanger. We also did put on flow meters on all the instrument air lines. There were pressure indicators, but they really weren't very good at indicating how much flow was actually being going through to the port. So we found a flow meter was a much better way to assure us that we had flow going through each of the instrument ports. Next slide. So the air permitting. So prior to the MACT rule, permitting was significantly easier. The unit was classified as a synthetic miner, and it avoided being a Title V facility. As a synthetic miner, you had emission limits, as shown there, 100 tons per year of each criteria pollutant and 10 tons per year of hazardous pollutants. And under the old rule, you only had to do testing maybe initially and maybe periodically, not that often. So this all changed with the new MACT rule that came out in 2011. All Sludge incinerators became Title V facilities, and they had to obtain Title V operating permits. So what this meant to owners of sludge incinerators was that you had strict emission standards on the 9 pollutants, and there were actually different emission limits for if you had a fluid bed or a multiple hearth, or if it was a new or an old unit. A new fluid bed had the most stringent requirements, and old multiple hearth at least. And Asheville being was classified as a existing or old fluid bed. It had kind of intermediate, I'd call it, but still relatively strict emission limits, very strict. So annual testing was now required. You had to do an annual stack test. And during that stack test, you had to establish operating limits on your pollution control devices. So during the test, you had to measure the pressure drop through the scrubber, the liquid flow rate, the pH, combustion temperatures, WESP, what its operating characteristics were, and the minimum levels during your test that you passed your emissions on. In the future, you had to operate above those minimum settings in the future. Slide. So more requirements of the new regulation. This was you had to submit a site-specific monitoring plan. You had specific requirements for your flow, pressure, pH monitoring, and temperature sensors. You had to assure that the accuracy of these instruments was they were accurate. You had to do an annual test by taking out the probe and seeing that your flow meter and your pressure was in fact an accurate measurement. And this was the same also true if you had an absorbent injection system, and if you had ash monitoring, there was requirements for that also. So more requirements of the Subpart L. Record keeping requirements, your operating data. Whenever you were in operation, you had to monitor all of your parameters, temperatures, pressures, feed rates, so forth. And you had to do operator training, an initial training of your incinerator operators. Had to pass a course that covered 9 topics regarding the operation of the incinerator. And all of your operators had to do an annual review training. Your reporting requirements, there was a initial compliance report, and then every year when you passed your compliance test, you had to submit an annual compliance report. It was quite a significant amount more of compliance. I'll turn it over now to construction, and Hunter will talk about that.
Yeah, thanks, Frank. Again, this is Hunter Carson with MSD. Talk a little bit about the pre-negotiations and the bidding. Since we had a very tight window for construction and meeting the MAC compliance date, we went ahead and either pre-purchased or pre-negotiated some of the large equipment. We did pre-purchase the heat exchanger, the primary heat exchanger, because it had a lead time of 9 months. The multi-Venturi from Fabricator didn't have quite as long a lead time, but it was significant. So we went ahead and pre-negotiated that, gave that proposal directly to the contractor in the form of an allowance. This ultimately shaved several months off of the construction schedule. We bid the project in February of 2015, and then immediately issued notice to proceed in March of 15. So basically had 1 year to construct the project and test to be in compliance for the following March in 2016. Our prime contractor was Heron Construction from nearby Tennessee. CDM also required in the specs to have a pollutant control system supplier, and this ended up being Industrial Furnace Company out of Rochester, New York. They did a wonderful job, but the purpose of the system supplier was to be responsible for installing, integrating, and ensuring that the fluid bed incinerator system was operational. Next slide. So here's some photos of the long-awaited equipment. You can see on the left, that is the new primary heat exchanger that we purchased directly from Thermal Transfer. On the right are pictures of the Envirocare equipment. Up top is the multi-Venturi unit. Far right or bottom right is the quench vessel, which is installed just upstream of the Venturi scrubber. And then in the center right is the mercury scrubber itself, which is positioned on top of the Venturi scrubber itself. So once the equipment was on site, our contractor immediately began installation of the new scrubbers. The multi-Venturi, as you can see, was a tight fit. This unit is close to 40 feet tall with the legs, and it was put in through that small overhead door there. So it was interesting to watch the installation. Actually, the mercury scrubber, which is the upper portion of the scrubber. It's about 20 feet tall. You see that in the center photo. It was actually installed first and then hoisted up towards the ceiling. The multi-Venturi was then installed through the door and tilted up, and both of those units were welded together in the field. Just a neat picture here in the far or the upper right. Once the multi-Venturi was in place, it was very difficult with a crane to get it exactly into position, so the contractor had a very neat way to move a heavy piece of equipment. They basically took sheets of Lexan or polycarbonate plates and used a lithium grease in between them to provide a very slick surface. They were then able to literally move it by hand into the exact position. So I thought that was pretty neat. Just some other photos of the installation. You can see on the left are the Venturis that are installed in the multi-Venturi unit, scrubber unit. The design accommodates 6 of these in total. I believe we have currently 4 of those actually in the unit. In the middle, you can see up top, those are our ash scrubber pumps. So those convey everything that is accumulated in the Venturi scrubber at the base of the scrubber, sends it to our ash clarifier. Down below that, there's quite a bit of water piping involved in this project. These scrubbers do require about 500 or over 500 gallons per minute of non-potable water, so a lot of piping involved. And then on the right is the mercury scrubber itself, and it's loaded up with the 16 SPC units and ready to go online. So sequence of construction, we did install the scrubbers immediately after arrival. Those are in that top red dot. That was the only open space, the only open footprint in our whole building. So we went ahead and put that in. But anything, the other components of the project being the heat exchanger and the ductwork, obviously had to be done when the unit was out of service. So there was a 40-day shutdown period associated with this that we had to work in. The heat exchanger was replaced. We did replace all of the ductwork, and then, as Frank mentioned, we added new skin or a new dome roof to the incinerator itself. So during this 40-day shutdown, we were hauling all of our solids to the local landfill here. This is just a schematic of our treatment process. You can see down below, circled in red, is the solids handling portion of our plant. So just downstream, after being dewatered, we did not inject into the fluidized bed incinerator, but went directly to our truck loading facility. Just some photos of replacing the heat exchanger. It is a very large unit, so it was craned, removed by a crane out of an access hatch through the roof. You can see it's about 40 feet tall there, that center photo. On the right, we're flying in the new heat exchanger unit. As I mentioned, all the ductwork was replaced. Kind of an interesting process here. The process started with a bare steel flanged pipe. It did have welded studs in the interior. IFCO, industrial furnace, they started by applying a mastic coating inside the pipe and then installed a high-temp insulation board. It was Insul Block 19. That was then fastened down with basically a large wing nut. And then finally, step 3 was to cast a high-temp refractory around the insulation block. So a pretty neat process, labor-intensive. A lot of ductwork installed. You can see upper left, a lot of man hours put into that. This was all the refractory lined piping, and this is essentially everything downstream of the incinerator all the way to the scrubber quench. So very high temp applications where temperatures range from just shy of 1,000 degrees upwards to 1,500 degrees Fahrenheit. There's a lot of stainless steel piping, ductwork as well for the lower temp applications. The photo you're seeing on the lower right there is coming out of the mercury scrubber. So this is just prior to being exhausted out of the system, but very corrosive gases, so hence the stainless steel piping. These are just some pictures of the incinerator dome replacement. The lower left photo shows a picture of or representative of what our incinerator looked like prior to this project. It was like a quilt. We had patches of steel all over the shell of the incinerator. So these are just photos of replacing the dome with new stainless steel panels. So IFCO did a great job getting everything installed. We were able to schedule a testing company to come in February in anticipation of the March deadline. We did test early February, and as you can see on the right there, we did pass and comply with all the MAC limits, but you can see the mercury, we just by the skin of our teeth were able to meet that limit at 34 micrograms. So we were a little concerned, and I'll talk about this a little bit more on the next slide. Basically, over the course of the next year and a half, close to 2 years, we honestly did struggle with this system. We really weren't seeing the results that we had observed with the pilot unit. Envirocare worked very closely with us, which we greatly appreciated. And we made a number of tweaks. I'm not going to go through all of these, but we made changes to the washdown procedures. We added a mist eliminator, kind of trying to remove some of the vapor barrier, or vapor carryover, I should say, to the SPC modules. Did a lot of changes to the wash cycles, even went to the extent of replacing all the 16 SPC modules, but that really didn't work. So if you progress another slide, please. So in working with Envirocare at this time, which again is about a year and a half after the initial installation, Envirocare did have another application that was achieving similar results to the pilot, about 90% mercury removal. So we were curious what the difference was. And we found out that that unit was running at about 30 to 40 degrees hotter than what we do here. So we were wondering if that was the key to the system's performance. Working, again, closely with Envirocare, they requested that we add some inline heaters, basically to boost the temperature just upstream of the SPC modules, and also to reduce the relative humidity in the mercury scrubber itself, which we did. Next slide. These are just some pictures of those heater units, very simple. They are 6 kW electric inline heaters, so those were installed to inject heated air just upstream of the SPC modules. And that seemed to be the ticket. Basically everything to the left of that red dot were the times that we struggled since the initial installation. However, everything to the right, you can see just an immediate improvement once those heaters were installed. We did start seeing the 90% plus removal rate and have been seeing that pretty much ever since. This is just another slide showing that data differently, but we have consistently been under the MAC limit with the inline heaters, so a very beneficial improvement. And with that, I'm going to hand it over to Ryan Dyson, one of our plant operators.
Hello, everyone. As Hunter mentioned, my name is Ryan Dyson. I've been a plant operator here at MSD for about 3 years now. I began as a college intern while attending UNC Asheville and studying environmental science. So I'm going to kind of provide the broad strokes for you operationally, just kind of the bird's eye view. This is a great screen to start with. This is actually our computer monitoring SCADA screen for the entire incinerator mass gas flow. So this is actually a depiction of the incinerator in its resting state, so to speak, as this image was taken shortly after the incinerator was shut down for the day. But it'll provide you a good visual depiction of the overview. If you look in the bottom left-hand corner of this image, you'll see what's labeled as FAB2. That's actually one of our fluidizing air blowers that provide a continuous flow of oxygen into the incinerator if we are burning. And we can control the airflow via this valve depicted to the left of that FAB. So we have 2 of those blowers, as I mentioned, one running continuously while we're operating and one kept as a standby. Just beneath this, you will see our natural gas line and all of the accompanying valves that we use to regulate our natural gas flow into the incinerator, balanced with our air in accordance with our sludge flow as well. Kind of still in the left-hand corner, but about halfway up the screen, you'll see what are labeled as SCP-1 and 2. Those are our swing pumps that actually pump the sludge into the incinerator itself. So number 1 here was bypassed when this image was taken as we were shut down. But those are our 3 primary components: the carbon source of the sludge from the swing pump and the oxygen from the blower and the fuel source of the natural gas, all flowing in, mixing together. We monitor our combustion chamber temperature continuously. As you can see here, it's 1518 is the average temperature. We have to be above, currently our site-specific limit is 1455 for our temperature. As he mentioned before, all of our specific parameters related to temperature, oxygen, scrubber differential pressure, water flows, etc., all come from our annual stack testing. So as we kind of move through here, the airflow is originally sourced from this FAB. But you can see right beside it, we have a temperature indicator that's showing 114 degrees at that time, which is quite significantly different than the 1518, and it would require us to use a lot more natural gas if we were just putting that cold, relatively cold air into the incinerator. So that air actually goes into the heat exchanger, where we have 2 functions simultaneously occurring, where you can heat up the ambient air, so to speak, and cool down the air that is leaving from the top of the incinerator and continuing to flow through the system. As you keep peering through in the temperatures here, you can see the temperature continue to decrease as it rises up and out of the incinerator into the heat exchanger. It goes from 1239 degrees at the top of the heat exchanger down to 663 degrees before going into the quench right here, where we just inject water into the airstream and keep moving down, and it's at 75 degrees here. Granted, this is at the incinerator's resting state before it goes into the actual scrubber system with the Sorbent Polymer Composite trays. We also monitor all of our water flows through this screen as well, and we do use reclaimed plant water from our facility to save significantly on city water, economically and environmentally as well. And we can monitor all the temperatures throughout, as well as our scrubber differential pressures, which you will see flashing there as scrubber differential pressure low. At this time, that was because we were not providing air or gas or sludge into the incinerator, so that's not an accurate reading. But as it continues to rise up, you can start to see closer to the ambient temperature as we leave the stack around 80 degrees. So go all the way from 1500 to 80 is pretty impressive there. I think that's good for this slide. Okay, so more detail as far as these operational parameters that we monitor and adjust. The airflow, typically between 4,800 and 5,300 CFM, although that varies seasonally depending upon the temperature of the air and sort of our oxygen demand within the incinerator. As pictured here, those are the FABs that I described to you. As mentioned before, we do adjust that based on our percent oxygen. We have to ensure that we do not go above 13.5% oxygen in accordance with our site-specific limit. So we have to make sure that we're providing enough oxygen for an efficient burn, but not too much to where we are not meeting our oxygen limit. We also may need to inject more air if our scrubber differential pressure is low, for instance. That also has to do with our natural gas flow and our temperature values. The more natural gas we put in, the more oxygen we will consume in the burn, and we'll have to adjust our airflow in accordance with that. And make sure that we're staying above our site-specific minimums in our combustion chambers as well. Next slide, please. Okay, so there's sludge flow. As operational staff, we always seek to maintain a burn rate of at least 1 ton per hour. This is primarily because that's the rate at which we need to burn in order to keep up with our sludge and our gravity thickener. Otherwise, we will be accumulating sludge faster than we would burn it off. Although we are currently permitted to burn around 2,500 pounds per hour, sometimes it's not feasible to meet that based on oxygen demand or natural gas flow, or really how much the press will hold when we dewater the sludge, as pictured to the right here. So those are all the different considerations that we keep in mind as we burn. Okay, we also monitor water flows, as mentioned before. Quench water flow, we usually keep around 135 gallons per minute. The condenser trays, that's where the majority of the water goes, about 360 gallons per minute, although we can adjust that. Venturi throat water around 25. And our mercury wash water, that one is actually city water rather than plant water, and that runs on an automated time cycle to run twice a day. So in terms of just general day-to-day operational troubleshooting, we need to maintain our scrubber differential pressure in an optimal range. Our site-specific minimum is currently 38.2 inches of water column. So if we are consistently dropping below that, we may need to increase our air, gas, sludge, and even water flows in order to raise that value up. If the readings are erratic, there may be some sort of trash or debris caught in the lines that are leading to the sensors that we could blow out with compressed air. And if the differential pressure is consistently high, we need to shut the incinerator down and open via those doors and clean those trays out, typically with a pressure washer is what we use. Okay, additional just sort of walk through troubleshooting. This was mentioned earlier, the lances and screens that provide the water for the scrubber system. Occasionally, the pressure gauges will indicate a clog, and we also do this just routinely as well, check to make sure that those screens are not becoming clogged up with any sort of trash or debris, because as I mentioned, we do use our reclaimed plant water here, so it's not fully up to drinking water standards, so we certainly make sure that there's no debris or anything of that nature clogging up those screens excessively. Okay, I also will flush this pressure port for our scrubber differential pressure sensor, because occasionally that will accumulate with a thick sort of ashy material and could give us erratic readings throughout the system. So I go to that yellow handled valve and flush that out safely on a routine basis as well. We also monitor our purge airflow streams. These purge air blowers are meant to provide air to keep our expansion joints cool and clear of ash and sand, so they run continuously even if we are shut down at the time. So each shift we go through and monitor via these gauges and rotometers at each joint where our airflow should be and adjust that accordingly. Just to give you an additional glimpse into our daily emissions monitoring, and this is sort of voluntary and kind of process control for us, in addition to our annual stack testing. We utilize a Testo 350 flue gas analyzer where we go up to a sample port on the roof of the stack itself and insert that in and test it. It's a 10-minute test for NOx primarily. NO and NO2 is what we use it for, but it will also test for SO2, carbon monoxide, percent oxygen. and we do make operational adjustments in accordance with those results. If our NOx readings indicate a high value, we may need to back off on our gas as long as we can with our temperature limit, or back off on our sludge flow and adjust our oxygen. We also do have continuous emissions monitoring systems for oxygen and carbon monoxide. So those readings are taken continuously and averaged out in one hour averages, and then used to calculate sometimes 3-hour averages depending upon what the permit requires. And we do daily calibrations of the oxygen carbon monoxide system via standard calibration gas tanks, and we keep track of that on a daily basis via daily roof reports that we monitor and keep on file here.
Okay, great.
So, yeah, I guess we'll wrap up with that.
Yeah, so now we can take some questions from the attendees. If you guys have any questions, you can type it in the attendee chat on the left-hand corner of your screen. There looks like there's already one question there. You guys want to go ahead and take that from William? Do you see where that question is?
Yes, about the continuous emissions monitors.
Yes.
My understanding of that, like the CEMs that we have for oxygen and carbon monoxide, there are certain parameters where it's not feasible to utilize CEMs. Oxygen and carbon monoxide, it's feasible to do that, but some of the other parameters where you have to measure down to very small concentration, the technology is not really widely available or feasible economically to test for those continuously, so those are often done via the annual stack testing. Someone might be able to elaborate on that a bit more than I could, but.
Okay, and then there's another question from Peter. If she wanted to elaborate, go ahead.
Hunter, you want to address that? I guess we have so far not to have to dispose of any membranes yet, right?
Just one sec. Let me hand the phone over to Hunter here. Sorry. One sec.
Okay, hello, this is Hunter. Brian and I are trying to trade off a phone line here, so sorry for interruptions. I think the question is about disposal of the spent SPC units. Actually, we have not had to dispose of any of them so far. As I mentioned, EnviroCare did come and replace all of the units approximately 6 or so months after the initial startup, but we have those in reserve. Actually, we did not dispose of them. We have them in storage, and so we're still seeing pretty high removal rates. Again, I think the ticket was to boost the temperature upstream of the SPC units, and so we've been using the same modules now for at least a year and a half, I guess since October 2017, I believe. So, yeah, we have not disposed of any units so far. When we do, however, they do have to go to a hazardous waste landfill, which I believe the closest to here is actually in Alabama.
I think that relates to Steve's question on the life of the SPC unit. I think the warranty says, what, 18 months or 24?
So this is Hunter. The guaranteed lifespan from EnviroCare was 24 months. That was guaranteed. The expected lifespan, however, was about 36 months.
Okay. Next question is construction. Hunter, you're just on the phone all the time. Just you can address this. Did you see the question? Yeah.
I'm reading through it now.
Yeah.
There were certainly risks involved. We did have the incinerator shut down for that 40-day period, so we were hauling sludge to the landfill, which took some of the risk out of the equation, but definitely had resident on-site inspector, and I was over there on a daily basis, so had a lot of inspection from plant staff and personnel here. We did have LDs in the contract as far as not meeting the 40-day required shutdown, because there was a significant cost associated with the hauling and disposal of the solids. Not sure if that answers the question entirely. Richard or Frank, I'm not sure if you want to step in on that.
Heat exchange and modifying the roof. Yeah, we just had, spec requirements really in there, but that was really all we did in that regard. Yeah.
Okay, moving to the next question. Why did you choose the Fabricator refractory depth on site?
I guess I'll take a stab at that. I think, maybe Frank, but that was, to be quite honest, I'm not sure if that was I don't think that was a spec requirement. I think it's something that Industrial Furnace or IFCO does very routinely. Do you happen to know, Frank?
I'm just thinking about that a minute here. Usually they have a shop, a local fabricator that's not too far away, and they'll do the refractory work there and then ship the pieces with the refractory in it. So it was a little bit unusual to have it done on site. Yeah. As long as you can maintain the quality, then on site is fine,
So the answer is it wasn't really a requirement. The contractor chose to do it that way.
Right. Yeah.
As far as the acidic water, there's a question about how the acidic water was disposed of. It's a very low volume. The washdown water from the I guess this person is David Ramirez is asking about during the pilot demonstration. We do have washdown water, of course, with the full-scale installation, but it's very small in volume, so it does go down to a common drain with the rest of the Venturi scrubber water, and we're talking on order of about 10 gallons per minute, but that's I believe Ryan hit on this. It's washed down twice a day. So mixed in with the volume from the rest of the scrubber being hundreds of gallons per minute, it gets diluted.
Yeah.
Okay, so there's one more related to shutdown and startup. You want to take that too, Hunter?
Maintaining contamination limits. Not quite sure on that one.
Yeah, I'd like to say a few things. The MACT reg does require that you meet emission limits during startup and shutdown, and we didn't really have too much of a problem with the contaminants that we were concerned with. I will tell you that at other plants, they've really had a problem meeting the NOx limit on startup, because if you have a continuous NOx monitor, then during your startup, you're supposed to meet that parameter limit, and I know plants have had a problem with that, and but that seemed to be the main pollutant that was giving treatment incinerators the problem during startup was the NOx. Yeah.
Okay, does anyone else have any more questions? Okay, guys, thank you so much. We're going to wrap up now, and if anyone has questions, you see the email on the last slide of the presentation. You can reach out that way. And that's about it. Thank you very much, everyone, and have a great day.
Thank you.
Thank you.